Hello everyone and welcome to our talk. My name is Pavel. In this video we'll present our paper RuMedBench, a Russian medical language understanding benchmark. With rapid progress in development of deep learning methods and their application to novel domains, benchmarking has become an important part of AI research. Domain-specific benchmarks set up industry standards and allowed guided search and fair comparison across available models. Healthcare and medicine is not an exception. In this area, perhaps the most known benchmarking dataset is the Mimic-3. It produces and supports many tasks, for example, prediction of readmission, length of stay, ICD code, next diagnosis forecasting, etc. But the dominant part of such tasks has been proposed for English, while for the other languages the number of similar research is much smaller. This is mostly due to the lack of available language-specific resources. First of all, such data deficiency affects the medical natural language processing area because of strict legal regulation of the industry. By our paper, we partially close this gap for language medical data in Russian. The design benchmark contains 5 tasks. You can see them on the slide along with some of their characteristics. 3 datasets and tasks introduced for the first time, 4 tasks adopted from English. To the best of our knowledge, this is the first such effort. We try to incorporate a diverse range of task types on a variety of medical text materials, so the benchmark can capture multiple aspects of the medical domain. All data and code publicly available in the GitHub repository. And now we discuss each task in more detail. I'll let Vladimir elaborate more about the first task.
Thank you, Pavel, and back to the task. We called it top 3 because the ultimate goal of the model is to predict the ranked list of 3 most probable diagnoses. Such a prediction has to be made based only on written symptoms and complaints from a patient. You can see a couple examples at the top of the slide. From this JSON element, the input field for the model is symptoms. Here and thereafter, we will show already translated sample for readability purpose. The source data for this task is anonymized notes from the electronic health record system. These data were collected during outpatient care in medical university clinic and freely available for scientific purpose. Formally, this is multi-class classification across second-level ICD-10 codes. You can see some of them on the slide. We limit the number of target classes to 105, dropping the samples with rare diseases, those that encountered less than 10 times in our dataset. For performance evaluation, we propose to use heated 1 and heated 3 metrics. The general formula for the metrics is on the screen, and you can see it is worth nothing that heated 1 is equal to accuracy. In the first list example, given the provided prediction, both metrics are 1, as the ground truth answer is in the list of 3 predicted codes, and moreover, it is in the first place. For second example, the only heated 3 is 1, as the ground truth diagnosis is in the predicted list but not in the first place. Averaging such value across all test samples gives us the final metric value. The model that decently solves this task has several practical applications. For example, it can be used in a clinical audit cycle loop for medical care quality control. Also, it can be used as a part of a clinical decision support system or even applied in automatic patient triage. That is all on my part. Alexander will describe the next task, and Alexander, I give you the floor. Thank you.
Thanks, Vladimir. The second task of our benchmark is about symptom recommendation. It's designed to check model's ability to recommend a relevant symptom given a specified text premise. By a symptom, we mean an explicit substring indicating a concept according to universe thesaurus. From a data point of view, this task is based on the same outpatient nodes as the previous one. But in contrast to the top 3 tasks, here we don't have a predefined ground truth label and have to prepare it in advance. For this, we use the text content and our internal tool for symptom extraction. Then, select a random term as the target one and strip it from the initial text. This process is schematically depicted on the slide. We start from the original patient node. Then, on step 2, we find 5 humorous symptoms. On the third step, let's say the body temperature, become our ground truth code, and the appropriate span is wiped from the original text. That completes the sample creation. Such a task can be viewed as a classification with 141 classes. Again, such a number of terms selected as a frequency trade-off according to the data. Some symptom terms are listed on the right part of the slide. As the task formally is close to the top 3, the same metrics are exploited for evaluation. From a practical point of view, the task is beneficial in symptom checker application, where the user interactions start with a set of incomplete medical facts. Therefore, additional refining questions about user symptoms enable a more complete view on patient condition, leading to accurate diagnosis. That's all for this task. Now Galina will explain the next one.
Thank you, Alexander. Above discussed tasks deal only with single input text, but more advanced NLP problems require the use of multiple inputs. The third task of our benchmark is exactly from such a category. Our firm belief is that the genuinely medical AI model should have knowledge and understanding of different health-related domains. Partially, this skill can be verified by checking the model's ability to answer context-specific yes or no questions. From here is the naming of current tasks consonant to those answers in Russian. A sample consists of 2 inputs, context and question. The slide shows a pair of examples from the development set. A context is an excerpt up to 300 words from a medical-related text. Such context extracted from different open sources. We tried to collect them from diverse fields such as therapeutic medicine, human physiology and anatomy, pharmacology, biochemistry, etc. To prepare the question, we involved a group of experts. Given a context, an assessor was asked to generate a clarifying question that can be definitely answered with either yes or no. All contexts are unique and paired with only one question. Moreover, the balance between positive and negative questions is kept, so the accuracy metric is well suited for this task result evaluation. That's all on the task. Now I will return the word to Pavel.
Okay, thanks colleagues. Moving on to the next task, which also involves paired input. Originally, the natural language inference task was proposed in early 2000s to research general linguistic phenomena. The objective of a language model is to compare a premise and hypothesis text and inference their relation is either entailment, contradiction, or neutral. Later on, in 2018, the task was adopted for the medical domain and called RuMedNLI. Again, the data source for the task is mimic-free records. The premises are extracted from the past medical history section of a clinical note. Hypotheses are generated and labeled by trained clinicians. This is excellent research that involved days of hard work by a large team of experts. It is hard to replicate such a pipeline from scratch for a new language, so in the absence of similar data and markup, we translate the RuMedNLI dataset to Russian. To achieve this, each text was processed by an automatic translation service, but on their own such results are poor because of domain-specific language, variety of abbreviations, mismatch of measurement system, etc. Many errors produced because of translation performed in a general context, not in medical one. For example, the phrase "delivery was a term" is seen as a message about post-package delivery instead of childbirth. Therefore, each sample has a thorough second look by a human editor to compile the final translation. It is worth mentioning that from almost 15,000 unique English text fragments, only less than 5,000 translations were left without any change. Based on this, we can estimate the automatic translation quality for the medical domain only as about 33%. Summarizing this task, along with data we inherit the original train-def test split and accuracy as evaluation metric. The translated data is available on PhysioNet through the mimic-free derived repository. Let's hear Galina again with a description of the concluding task.
Thanks, Pavel. Our last task is about named entity recognition. From all presented ones, perhaps this is the most traditional and well-studied, but nevertheless, we incorporate it in our benchmark for broader machine learning task types coverage, as this is a token-level task. From a practical point of view, such fine-grained analysis is required in downstream tasks, for example, in relation extraction or explainable AI methods. Unlike the previous tasks, this one even has readily available open datasets for Russian, so we base the task on existing data from RuDrag corpus. For naming consistency with previous tasks, here we call it RuMedNLI. The data are user reviews about drug products from a popular internet resource. Each review annotated with 6 types of named entities: drug name, class and form, adverse drug reactions, drug indications and symptoms of a disease, and the last is findings, a kind of a miscellaneous type for an entity. The current slide presents such a review example with some of those entities highlighted. In total, across the dataset, there are about 4,500 entities stored in IOB format, meaning each token is marked with one of 6 types or labeled other, in case it doesn't belong to any category. Formally, this is a multi-class per token classification, but classes are significantly disbalanced. That's why the evaluation, along with accuracy, we compute F1 score. That's it. Now I return the word to Pavel, so he will describe results of baseline models and make the final conclusions.
Galina, thank you. To test the created benchmark, we applied several baselines from essential NLP approaches, as well as perform human evaluation. You can see the results on the slide. The first line is the naive method with assignment of the most common label as an answer. Such a method gains some performance in tasks with unbalanced label distributions, but works like a random chance for question and inference tasks where samples have equal proportion for each label. In the second baseline, we mostly use the TF-IDF weighting scheme for feature extraction, followed by a logistic regression model. Exception is the named entity recognition task, where we applied the conditional random fields model to process handcrafted token-level features. To our surprise, such traditional methods showed decent performance in the first 2 tasks, even taking the absolute lead in the first one. Chronologically, recurrent neural networks are the next group of powerful methods to tackle NLP problems. So we picked the bidirectional long short-term memory neural architecture to implement as our third baseline. But results are only slightly better and only for the last 3 tasks. And lastly, of course, we couldn't ignore the trending transformer architectures. We implement a couple of BERT-based models. The first is a vanilla version of pre-trained Russian BERT with 110 million parameters, and the second is its modification with change in pull-in strategy. Both methods yield significant improvement on the last range of tasks and come close to the best values in the first two classification ones. To come up with the single numerical characteristic of the benchmark, we propose to infer the overall score, which is the mean over individual values. Therefore, you can see that BERT baselines are the strongest among the tested ones. As already mentioned, to get an idea about human performance, we also solved the same set of tasks by a group of assessors. You can see their performance in the last line. It is interesting to note that clinicians have completely lost to the models in the first two tasks. We discussed the result with them to clarify this finding. It turned out that during labeling, the main concern and source of errors was insufficient and noisy information provided in the text. It once again confirms that not only symptoms, but gender, age, anamnesis, and lab results are essential in medical diagnostic tasks. Without such detail, a model is a better conditional estimator or statistical distribution over many target classes. But human intelligence holds the lead in the tasks that involve more knowledge and deeper understanding of the subject and language. For example, the question answering task is the most challenging one, with a gap of more than 20%. We hope such a lag will be reduced after more advanced and specialized Russian medical models appear. That's about all on the baselines. We believe our effort in such a benchmark creation will be beneficial for the NLP medical research community. From a purely academic point of view, this is an exemplary use case of non-English benchmark construction. Some tasks are ready to go, but the formulation of medical diagnostic ones should definitely yet to be clarified and improved. From a practical point of view, we hope our work will provide a solid basis for data practitioners looking for open datasets and novel tasks in Russian. Also, proposed tasks can find the use in broader testing of existing multilingual models. At the end, we want to thank anonymous reviewers for their insightful comments and conference organizers for their effort. And thanks for your attention.